Okay, I'm going to be working predominantly today off of the OneNote, so I'm probably going to be sitting down most of the time here, but let me just jump in here, bring OneNote up here. Where's my OneNote? So sending, usually, where is it at? I don't see it. There it is. Okay. No, I'm not connected to the internet. I've got this thing stores all my notes on in the cloud. Okay, well, we'll just go ahead and get there. Starting next week during the tutorial sections, does everybody have one of those little prototyping boards that you use in your electronics courses? Everyone should have one of those. You'll start needing to bring that with you. Because what we're going to be doing is I'm having all these boards modified to put on the bottom of there's a connector here where you can plug it into your prototyping board so we can start interfacing to the board. So the lab starting next week will require that you have your board that you will then place this in here. Now, unfortunately, I'm old enough I need to put my glasses on to read this here. But let me just kind of talk a little bit about this. As we look at this board here, and I'm looking at this, well, let me just kind of draw it here. Right here's the top of the board here, and it's like this right here. As we look around this, the top one is ground, and I'm not going to list all these here, and then over here is ground. This connector has got 22 pins on it, is what it has. And then as we go around this right here, we'll see port 1.4 all the way down here. The last one is port 0.3. Over here it's 0.2, and it works its way around 2.1 right there. So in order to access the ports on this board, you just simply plug this into your prototyping board I bought a bunch of 220 ohm resistors and excuse me, along with some LEDs. For right now, we're just going to use resistors and LEDs. I hope to get some temperature sensors as well, so we can use the analog ports. If we don't get temperature sensors, we're going to do an experiment using the analog port and either the potentiometer on this or a potentiometer that's there. So we've got a few labs ahead that are going to be using this board, and I'm really going to concentrate most of my lectures on the gearing up to the labs. That's not to say that the material I'm covering that it's going to be covered, we're going to be doing labs on, will not be on the final exam right there. So with that said, I did not write the lab yet for the interrupt, but I'm going to go through it with a C and we can modify that fairly quickly. But I'm going to just kind of spend today a little bit talking about finite state machines and where we're going with next right there. So my throat is, some days I don't know why I'm a little hoarse this morning, but we'll see that there. But again, we've got about, I counted about 6 weeks of classes left, about 5 weeks of classes. So we've got enough time to do the labs that I want to get done. But we're going to be concentrating on doing labs for the next 3 or 4 weeks. Which is really the more fun part. Yeah, that's there. So today what I want to kind of do is I want to lean ourselves toward our mini project for this class. And our mini project is a fairly simple one. It's going to be a stoplight, right there, controller, right there. And we're going to be doing that in C. Now, in the meantime, we're also going to be doing a couple of other small projects, where we're going to be basically learning on using the analog port. But before we do that, I want to get you started on the mini project right there. Thinking about that there. Again, it's not a very intense one, but it's one that's worthy of talking about. So with that said, and somehow my interface looks different today, but right there. Okay, well, let's talk about what a finite state machine is. And I'm going to pop the keyboard off here. I don't really need it today. Is a finite state machine is basically a way of looking at a process in terms of states. Now, a state is a particular condition in which you're in. Now, I'm going to use for an example here something like an elevator right there. An elevator is a finite state in that it's got basically, we'll look at the elevator here on this floor. This building has got, 8 floors right there. So it's got 8 states. We're going to assume, we're going to ignore the process of moving from one state to the next. That's there. So when we look at this elevator and up, that's there. I wasn't the last one in class today. I was running late myself, so that's there. Let's make it simple. Let's just look at a small building. When I say a small building, let's look at one that's got, say, just 3 floors. So we've got 3 states. Here's our building. Here's our elevator. It can either be on the ground floor, the first floor, or the second floor, right? Right there. So let's assume that this state, so we have 3 states. Right there. Oh. We'll get it, I'll solve that there. So as we look at that there, and let's just draw these states as little bubbles right there. So if we're in state ground, right there, state 1 and state, and all right, now where did I get myself into? Right there. Oh, that's not the right one. I'm really having trouble with my Outlook. Where's OneNote? There's OneNote. Okay. No, now we got something, a different interface. My computer is not cooperating very well today. All right, getting back to where we were at. We have 3 states. We have ground, 1, and 2. Those are our 3 states. Now, where can we go from the ground floor? We can't go to the second floor directly, right? We can only go to the first floor. From the first floor, where can we go? We can go to ground, or we can go to second. Where can we go from the second floor? Back to 1, right there. So those are the state transitions we can have. Now, what we want to look at is how do we get from ground to 1? Well, let's assume that we have 2 outputs of our controller. So output 1 is up. We're going to assume up is a controller that tells a motor to go up 1 floor. So we're going to go up. We're also going to have another output down. Yeah, probably that there. We also have multiple buttons within our system. We should have 3 inputs that are going to say G, 1, and 2, right? Those are the buttons on your elevator, right there. And we'll also assume that there's also 2 more buttons, and I'm going to call it UA and DA for the down and up arrows for the controllers. So we have 5 inputs right there. So inputs right there is 1, and I'm going to spell it as 1, 2, GND, UA, and I'm going to go ahead and spell it, U arrow, D arrow. So those are our inputs to this system right there. We have 5 inputs to this system out there. And as you think about an elevator out there, designing the microprocessor control for it, this is the process you want to start thinking about: is what are our states, what are our inputs, what are our outputs right there. We define those. The next thing we want to do is start defining the conditions in which we move from one state to the other. Now, I personally like to do that with a table. Some people will do that here. But I like to just kind of list the states and then start. And the reason I like to do it with a table instead of on the finite state machine drawing, although I'll go through that method as well, is that I'm going to translate that then onto C code right there. And you'll find is once we specify how the system works, writing the C code for this becomes a very easy process. That there becomes very straightforward. So let's go ahead and start this table here, right here, and right here. So what's our first state? Our first state is ground, right? Now, we can only do 2 things in ground. We can either go up to 1, so our next state, and I'm just going to write this here as current state, right there, that's a current state. This is our next state. Next, right there. And actually, let's do it this, let's just use, keep the same end state right there. And then the last column that I'm going to put here is condition. Right there. How do we go there? So from current state, from the ground, we can go to ground. Right there. In other words, we can stay right where we're at. Right there. So if we're staying right where we're at, that means that the U arrow and 1 are both equal to ground, or 0, right there. In other words, they're not active. No one's pushed either of those buttons right there. If someone pushes the down arrow, that there, or, and I should put and 2 equals ground, right there. I forgot the fact that you walk in the elevator and you hit 2 when you're on the ground floor, which means that you want it to go on to 1 right there. Now, one of the things we're not really talking about here is that I'm simplifying this problem for right now. You know, one of the things that you would do is when you push the 2 button, for example, you would then latch that. You would keep that on as part of your machine. We'll talk about how we do that later. For right now, I'm ignoring that. So when I push the 2 button, we want that button to stay lit until we reach the 2nd floor. Right there. So that when we get to 1, that we know that the 2 buttons already been pressed, and we're going to go on. We're going to stop at 1 or not stop at 1. So it's one of those cases we could essentially go straight from ground to 2, but for this simple example, I'm going to ignore the fact that we're going to stop at 1 and go on up to 2. I'm not trying to design an elevator. I'm trying to teach the process. So there's lots of little steps that you're going to see that I'm kind of leaving out right there. So for right now, I'm going to assume, and I'm going to erase this and 2 equals the ground and ignore the 2, just simply to make our design simpler. So So right now, we're going to assume that this is elevator Bodo, that there is that if I want to go from the ground to the second floor, I got to get up and press 1, wait till it gets to the first floor, and then press 2 again. So this is elevator. This is a stupid elevator. That there. Bad design, but it was designed by a class of a student versus that there. But later we can go ahead and we can improve this and fix those problems. That there. So all right. So that's that there. So we can also go to 1. Right there. Actually, and the way we go to 1 right there is again the U arrow. Actually, you know what? The U arrow will just bring it to ground. The up arrow will bring it to ground. Yeah. The down arrow we're going to ignore. So the U arrow is a button that somebody presses to bring it to ground. That there. So actually, as we look at our elevator, and as you well guess, I came into this class. This will be posted on YouTube. Everybody will know it without designing this problem first. So I'm designing it from scratch. I've done this problem before, but not this early in the morning, and not before at least 3 cups of coffee. So let's think a little bit about this problem. And this is not an unusual situation when you start a problem, right there. It's I jumped right into the design without analyzing the problem. And that's a very common mistake, and you may as well watch me do it because you're going to do it. You go out and get a job, and you go to work for, Putri Elevator Corporation. You're designing the controller. You're going to start writing the table, and you're going to realize, hey, that's not going to work that way. So go back and let's look at our problem right there. And when we look at our problem right here, let's look at our problem. We're on the ground floor, right there. We want this elevator to move. The only way this elevator is going to move is if somebody, and here's the problem that I have. And this is that I'm treating this elevator very stupidly in the fact that I don't have 1 up button, I have 3 up buttons. I don't have 1 down button, actually I have 2 up buttons. Let's look at the elevator system. On the ground floor, you have an up button, right? This is outside. On the first floor, you have an up button and you have a down button, right? On the second floor, you have a down button right there. So the number of inputs, I was wrong. And if I was taking a final exam on this here, if I would have kept going down that path, I would have lost marks right there. And by the way, that should be a hint right there. Is that you might see something like this on your final exam. So as you look at this right here, right there, we have to realize that we've got 4 arrow buttons that we have. So let's name them as G up. I'm going to use it up 1, down 1, right there. Let's keep it consistent right here. Right here. Let's call it, I know you guys are writing this down and you're at there. And this is up, ground, on the ground. This is down 2 right there. So we now have 5 buttons we have to consider. That there. Inside the elevator, we also have 3 buttons. So this is on the floors. If you walk up to this elevator right here on the ground floor, there's no down button, right? There's only an up button. Because where are you going to go? This building has no basement. You're on the 8th floor of this building. There's no up button because where are you going to go? On the roof? This building has no roof access. So in our small 3-story building, we only have an up-down button on the only floor that can go up and down. So this is where I didn't look at the problem properly the first time. Right there. Fortunately, I caught this before I was 2 weeks into the design process. Sometimes we've gone a week or two into the design process, and we realize that we've made this mistake. And believe me, I've gone for projects, we have gone much farther into the design process and realized we've left off an input or an output. That's there. So this is not a common mistake that happens. So inside the elevator, we've got 3 more inputs: 1, 2, and ground. They're in the wrong order there. The ground should be on top. So we've got a total of 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 inputs. Right there. So we've got 7 inputs that we have to deal with at this particular point. There. So when we go through this process, we're going to look at the fact that we need to look at how these 7 inputs affect our state transition. So I'm going to go back to that process I started here, and let's say we're on the ground floor and we're going to go to the first floor, and we have to look at each of those transitions and look at each of those 7 inputs and how they affect that. Some will be I don't care. But let's go through and let's look at this transition right here. So if we're on the ground floor, the first thing we could do is we can go to, again, the ground floor, we only have 2 places we can go to. Ground, that's there. Ground, right there. So to go from ground to first, and we'll handle the problem going from that there. We're going to go from ground to ground, and the only way that we're going to go from ground to ground is if really none of the buttons are pressed, other than if inside there's somebody in the elevator and 1 is pressed, we're going to go to 1, so that has to be a 0. If somebody on the first floor, down 1, presses that, then we're going to go up to pick that person up, right? If somebody on the first floor presses the 1 button, the elevator is going to go up to the first floor to pick that person up. If somebody on the second floor presses the down button, the down button, we're going to go up and pick that person up, right? And if the 2 buttons inside the elevator is pressed, we're also going to start moving up towards 2. Now we're going to go to 1 in this case, but we're going to go ahead right there. So as we look at this here, we can ignore inside the elevator. So I've got 5 inputs. These all have to be ground, right? So we can ignore the ground button inside the elevator is a don't care. We don't care about that. And what other button? That's there. The 1 button, the up button inside or outside that there, will bring it back to ground, so that's a don't care. So up G is a don't care. All that's going to do is open the door. And we're only controlling the elevator going up and down. We're ignoring the door for right now. That there. Again, we're trying to get the processor. So these are the conditions in which we stay in ground. If any of these inputs change right here, these 5, we're going to move to 1, right? Right there. If somebody in the elevator walks in the elevator, presses the 1 button, the elevator is going to start moving. Now there might be some other logic we add later on to control opening and closing the doors and waiting. That there. We're ignoring the open and close button. As I said, this is elevator Bodo. That there. So in other words, we're just trying to get the simple logic on how an elevator works. That there. And you start thinking about something as simple as an elevator, it gets pretty complicated very quickly, doesn't it? Not there. It gets very complicated very quickly. So if we hit the down button there on one, the elevator is going to go up to the first floor to pick that person up. If we hit the up button on one, we're going to go to the first floor and pick that person up. If we hit the down button there on two, the elevator is going to go up to that floor to pick that person up. And we hit the 2 button, we're going to start moving up toward the first floor. So those are our conditions. So if any of these buttons are pressed right there, we're going to go to 1, right? So ground to 1, and I'm just going to go ahead and just call it, I'm going to change my names here a little bit simply because I would just call this state underscore ground or 1. I'm going to change my syntax a little bit here, and I'm going to put an S in front here, S underscore, and the S is just a way of saying S underscore means state right there to separate that from inputs and outputs, because a state is not a variable, it's a particular state right there. Later on we could, have you looked at enumerated lists in C? Does that sound familiar? I don't think I'll talk about it today. I think I'll probably wait till next week to kind of finalize this whole discussion here. But okay, so that's there. So if we look at this here, and if we were to look at this here, and I'm jumping ahead a little bit, but if we were going to look at this situation here, we've got our inputs right here, and so what we're going to say is let's take our inputs right here. We have, what do we say, 7 inputs right there, and let's put them into a, right there, 0, 1, 2, 3, 4, 5, 6, 7, and let's just say, for sake of example, we're going to put those on port 0, which is what you would want to do if we're going to put this into a microprocessor. I'm kind of jumping away from the process a little bit, and let's just define where each of these are. And again, this is very similar to what the 8051 does in the special function registers. Each bit has a particular location. So let's go ahead and put here, and I'm going to try to write here. I don't know how well it's going to work, but let's just go back to right here. These are our 7 inputs, and let's just kind of start at the top right there. Let's just put all the arrows first, and then we'll put the 1, 2, 3. So let's just go back to here. Oh, now what mode am I in? Okay, so right here, our arrow. So we're going to call this one G up, is what I call that, right? We're just going to call this up 1, down 1, right there, and down 2. So we look at that right there, and then we're going to just call this, and I'm just going to go ahead and just put, these are our three buttons inside. What did I call that? GA? Just what? Yeah. I call it 1, 2, and G. 1, 2, and G. Okay. All right. So let's just call this G and D. This 1 and this 2. Okay. Up there, and this is not used for anything right now. So that's where we're going to be putting our, that there. So what we're coming up with is a fact that now we have to assume that we can have multiple key presses in the real world. This is an academic exercise, So we can assume elevator Bodo doesn't let people press two buttons at the same time. Right there. In the real world, that does happen, right? Somebody on the second floor pushes the down button at the same time someone presses the two button inside the elevator. But we're making some assumptions again that if we're doing a real elevator, that would make our problems much more difficult. I think everyone can agree this problem is getting difficult enough. That there. So you can see why somebody like Otis that designs elevators takes a long time developing the controller, because they have to cover every possible scenario. It's not a trivial process. You as engineers, sooner or later, will be in the process of possibly designing elevator controls. That's one of the things that engineers do. This is not a microprocessor system per se as you look at it, but it uses a small controller to control the elevator. So this is very, very much in the line of something that you may be doing. So as we look at this right here, so going back to our previous slide there, we can look at this here and we can assume for case that we're going to assume that this is always going to be 0. For our case, always ground right there. There. And we can assume that very simple since we're designing this, we just simply ground it, right? Not there. Not there. Or we can always end it with 120, not 120, whatever, 0 and all 7s right there. We could, when we read the port, we can always set it to 0 if we want to, right there. So, but we can assume for sake of our discussion there. So we're going to ignore some of these inputs there, right there. So let's go back to our previous slide and look at right here, right there. So when we read this, so we're going to say inputs equal, and we're going to say port, and then I connected that to port 0, right? And then we're going to AND that with, right there, and we set this up in what order, and that's what I get from right there. So the bits that we want to be that there, and before I do this, let me cheat here a little bit. And I want to, yeah, I've known how to do that before, but let's turn the draw off. Yep, maybe I can't. The old version of there, it was easy to just draw a circle around this and copy, so I didn't have to rewrite it. Is what I was trying to do, but I don't see the select. Right there. Nope. Nope, it's still in that mode. Okay. All right, never mind. We won't do that. So what we're looking at here is that the up arrow is a don't care in this case, right? So I'm going to redraw this right there. The up arrow is a don't care because it's already on ground, so we don't care about that one, right? D1, we care about that one there, right? So that one's got to be a 0 in this case. U1 has to be a 0 in this case. D2 has to be a 0 in this case. Ground, right there, that's the elevator's already on the ground floor, so that's a don't care. 1 has to be there, and 2 has to be there. So when we look at this here, we convert that right here, and what we want to do is we want to 0 these out there. So how do we 0 something? Is we AND it with something with those as zeros, right there. So if we do an AND operation, we can 0 that out, right there. So if we go ahead and put 1, actually we want to keep those is what we want to do. So what we want to do is we want to get rid of the don't cares in this particular case. So if we put 0, 1, 1, 0, 1, 1, 1, 0, if we AND it with that, and that turns out to be 6, and I can't think real quick what that is. Where's my... Yeah, let me pull out my other calculator here. As I said, I don't know what's going on here with my binary 0, 1, 1, 0, 1, 1, 1, 0. Convert, that's 6E. Right there. That's 6E. So what we want to do is we want to AND that with 6E. Right there. And right there. In order to get rid of the 2 don't cares. Or the 3 don't cares in this case. So we're going to get rid of those unneeded inputs. And then if it's anything other than that, we're going to go to 1, right? Going back to my previous discussion, if any of these are a 1, we're going to go to the first floor. If somebody in the elevator hits the 1 button, we go to the first floor. If somebody on the first floor hits the down button, we go to the first floor. If someone hits the up button on the first floor, we go to the first floor. If someone on the second floor hits the down button, we go on up to the, we're going to go, eventually go up to the second floor, but we're going to go to the first floor first. If someone hits the 2 button in the elevator, we're going to go on up to the first floor. So what we're going to say basically is we're, in our C code, we're going to look at our state, and we're going to say if we're in this state, let's say our next state is going to be 1. So we can write a very simple C line for this, and I don't know if we're going to get through it today, but I could look at this right here, and I could say if current state equals state C, or ground, right? Right there. If port, I'm going to say, let's go ahead and, before I do this, and again, I'm writing this off, our code may look a little different. I'm just trying to get a point here. Before we do this, somewhere up in here, we're going to have inputs. Well, actually, no, at this particular point, let's go ahead and read the inputs here. We're going to say inputs equal port 0 ANDed with 0x6e. Right there. So we're going to go through and look at that there. If inputs is anything other than 0, we go to state up there. If inputs not equal 0, then we're going to say next state equal 1, right there. And close our end up. So we have this very simple statement right there that just simply is going to look at our current inputs and say what our next state's going to be. Now later on, as we're writing our code, we're going to find that this is gets fairly straightforward as we look at this right here. So, but we're going to, if inputs is equal to 0, our next state is going to be what? I actually didn't finish this right here. I need to add to this. And actually, let me move this to a new screen here. Let me write this to where it's readable. So we're just going to say if current state equals C state or C ground, that's ground. Now later on we'll talk about how we set C state is equal to S ground. Up above, we'll set up an enumerated list or something like that, or we'll just define these as constants up above, right there. But we're just going to make our code easier, instead of saying states 0, 1, 2, 3, I'm just going to say, give them names. It just makes it easier. So at this particular case, if we're in this state, our inputs that we care about is equal to port 0 ANDed with 0x6e right there. So all we're going to do is we're going to read the port and see what our inputs are right there. If our inputs are all 0, then we stay in the current state. So if inputs not equal 0, right there, then we next state equal S1. Is that what I called it before? Else next state equal S ground. We stay on the ground floor. That handles our state transition from ground right there. Now we repeat this process for all 3 floors, and we're not done with it. But do you understand where I'm going with this? Is what we're doing is we're looking at our inputs, and we're deciding what we want our next state to be. And when we decide what they are, we just simply write our C code that will handle this. Now, granted, we could write this in assembly language. I think you can imagine this is messy enough in C, right? Trying to write this in assembler would be how much fun? That there. Do we have the rest of the semester? That there for this simple example. So let's go on and look at the next state right there. Right there. So our next state is we're in S1. Right now, S1 is a little bit more complicated because we have 2 places we can go. This is probably our more complicated one. So in S1, we can go to ground. Right there. At there. We can go to S ground. In other words, we're going to the ground floor. Under what conditions do we go to the ground floor? Well, if somebody, again, we look at our 7 inputs right there. So we got U ground. We've got, D1, D2, up 1. Excuse me, there's no, in D2. Those are not in the right order. We probably should put them in the order of our inputs. Let me go back. And the order our inputs are what? Up ground. Where do we put? Okay. All right. So I want to try to help me out, folks. I need to try to keep in this order. UG, that there, because it makes life easier if we keep this order right there. Normally, to be honest, when I do this, I have 2 monitors there, so I put one side on one monitor, one side on the other monitor. I don't have the luxury of having multiple monitors in front of me here, so that there. So as we look at this right here, so it's okay, and I call that GU. Yeah, that's right, GU. I kind of reverse that. I should keep that consistent, but we'll work with that. GU. GU, and what was the next one? D1, U1, D2. What's that? Oh, G and D. 1 and 2, right? Right there. So those are those are our inputs. And again, that was why I was going to try to last through that first one, so I didn't have to remember that. I could just stick that on every page before I started working that there. But this version of OneNote, I haven't mastered that. So, so if we're on ground, that there, if somebody on the ground hits the 1, is it going to go to hits the up button? Is it going to go to ground? Yes, right? So this has to be, this is a 1 right here. If someone hits the down button on 1 or the up button on 1, we don't care. We're already on 1, so those are don't cares, right? If somebody hits the down button on 2, we're not going to go to ground. We're going to ignore that, right? Right there. or excuse me, we're not going to go right there. Actually, that has to be a 0 right there. I'm just going to say that that's not going to take it to ground. Somebody hits the ground button on the elevator, then of course that's going to take it to ground, right there. Somebody hits the 1 or the 2 button, it's not going to go to ground, right there. So we're only going to go to ground if this button is pressed or that button is pressed. And again, we're assuming that we can't hit 2 buttons at the same time. That's there. If we hit 2 buttons at the same time, then we have to go through another algorithm of saying, all right, if we're already going up, let's just keep going up, and then we go down. That's there. So we can make this much more complicated. We could probably spend half the rest of the semester on just this problem. And I've done that in some courses, that where we spend half the semester solving this problem, and we get tighter and tighter to the final solution where it looks like a real elevator controller. Right here, we're just trying to get to the basic concept of how an elevator controller works. So if we look at this particular one there, those are the conditions that we're looking at right here, and these are don't cares right there. So we're going to simply AND that up there, and we can look at either of those bits. We can look at the bits directly there, or we can just simply do a OR right there and say if we're in this state, and then we can have the if right there. So let's then go to the next state. Let's just leave this here and keep working on the same page here. So if we're going to go to state 2 right there, we look at the state, we go through the same exercise right there. And I know this is a tedious, and this is why a lot of students hate software, because you have to look at these things at each input one by one to decide. It's not difficult. This is not difficult. Boring, yes, but not difficult. Right there. All right, S2. Under what conditions do we go to S2? Again, we look at the same inputs. GU, D1, U1, D2, GND, 1, 2. Now, actually, at this point, you might be able to just jump ahead and guess which ones they are, but I'm going to go through them one by one again. Right there. So, somebody on the ground floor hits the up button. Are we going to go to the second floor? No. So that's a don't care, right? Somebody on the first floor hits any button. We don't care. We're already on the first floor. Somebody on the second floor hits the down button. Then what do? We go up to the second floor to pick them up. So that's got to be a 1. Somebody hits the ground button. We're not going to go to ground. Right there. We would have covered that in the previous statement. We'll go to ground. So that's a don't care. If somebody hits the 1 button, we don't care. But if somebody hits the 2 button, we go to 2. So you can see it gets a little quicker as you go to the second one. So as we look at this right here, we're going to sit there and we're just going to say if our current state is equal to S1 right there. Right there. And we're going to just stick this, and this is actually what our code's going to look like right there. Now I'm going to read these ports within the individual, because this is a little bit more complicated right there. I'm going to have a nested if then else. I can use a switch, and we'll look at using the switch later, right there. But we can look at, say, if, right there. There. First off, let's go ahead and get the inputs. And I'm going to do this a little bit differently than the first one, is I'm going to just simply say inputs equals port 0 right there. I'm just going to read them, and I'll do the and within the right there. So the first one is if, and I'm going to say inputs ANDed with, and we didn't do this up here, but again, this is in this order right here. 1 x x right there, x 1 x x x x right there. So we're going to AND that with 1 1 hex, right? So if inputs ANDed with zero x 1 1 right there, not equals 0 right there, then our next state is equal to state ground right there. And actually, I'm going to leave that semicolon off because I'm going to stick an else in here right there. You know, see, if I put a semicolon in there, you know, it's going to give me an error when I stick this else here. So else if, right there, else if inputs ANDed with, and again we come back right here and we look at we do the same thing, and we go x x x 1 x x 1 x, so that's going to be 8. Because we're going in the reverse direction, I'm reading this from bottom up, right there. I stuck the extra x there because we're that's why there's an extra x here for bit 7. So that's going to be 4 at this point right there. So 8 4, right? Or 4 8, excuse me, 4 8. If we put it back in this here, it would be 4 8 right there. That's why this one's so important. This table right here is that there. You really need to put it back into this table to come up with that. Instead of redrawing that table for everyone, which would keep us here till 11:30 before we finish this one here, right there. But going back to this right here, let me just go ahead and make sure we got this right here. So this is G up. This one was what? D1. U1, D2, G1, 2, and don't care. So as we look at this right here, this is don't care, 1, don't care, 1, don't care. So this is, oh, I'm off by 1 here somewhere. Right there, I'm off by 1. Is that right? G1, D1, U1, D2, is that right? This is G1, 2, ground. So G1, that there. D2 is the one that should be. Okay, I did this one wrong here. This should be the one here. And then the 2 button should be that there. So that becomes 4 8. Okay, 4 8. So 0x 4 8 right there. If that's the case, we're going to say next state equals S2. And we still don't put the semicolon in because we then have to put the else end state equals S1. We stay in the same state right there. And we need to put a bracket here and a bracket here to end that if that else. So as you can see, this is a little bit messier, and that's why later, as our problem gets a little messier, we're going to convert this to a switch right there, because the switch actually is a much better tool for that. Because if we had 5 different transitions, this if then else would then have 5 else conditions. Here we have 3 possible states to go to from 1. You know, we could go to ground, we could go to 2, or we can stay in 1. No, when I go back to my original state transition, right here, what I didn't show is that we also have this possibility on each one of these right here. I did not show that right there. Is that we have the possibility of staying in each state. So we have that there. We don't always have to go to another state. Some state machines you have to. Right there. Other state machines you don't. That there. So, oh my time, I've gone about an hour. All right, let me just continue on, and let's just look at the second floor right there. And because once we do this, what we haven't taken care of is our outputs. All we're doing is looking at our inputs and how we transition the states. I prefer to do them separately. You know, because we go through this table here. Yeah, let's finish the problem, then we'll go on right there. Okay. Let's go to the last one is state 2. State 2 is simpler than state 1. Our most complicated one is state 1. And the reason state 1 is more complicated is we have multiple possibilities. State 2, we only have 2 possibilities. One is we stay in state 2 or we go to state 1. Right there. So if we look at it again, I'm going to put this over here just simply so that we have that there. 4. And this one is UG. This one is D1, U1, D2, is that right? This one is 1, or G, ground. This one is 1. And this one is 2. Right there, and this one is don't care. Does that look like what I had to begin with? Okay. I just find it easier if I have that to look at when I start writing the code right there. So again, as we look at this right here, and I'm going to just simply write, I'm going to take a shortcut here, and I'm just going to write the bits across here. So if we're going to be looking at going to S1, what are our conditions? We don't care about the first bit right there, because that's I don't care. If we hit the 2 button, where do we go? We're already on 2, so we don't care about that button. We don't move to state 1. We hit the 1 button, we definitely want to move right there, right? If we hit the ground button, we want to move, right? If somebody hits the down button on 2, we don't care, we're already on 2. If we hit the up button on 1, then we're going to go to 1, right? Go down to 1 to pick them up. If we hit the down button on 1, we're going to go there. And if we hit the 1 button on 2, or on the ground, we're going to go down and pick them up. So as you can see that to go to S, there's multiple ways we're going to go to S1, right there. Multiple ways we're going to go to S1, that there. So this is what 3, 7 is what that is. So if you, personally, I find it easier to do it this way than the way I've been doing it. But I did the way that I did it earlier just so you can see where I'm going at. But all I'm doing is I'm looking at this bit here and I'm tying it to right here. I'm looking at this bit here and tying it to that there. So by having this on the right-hand side, I can actually just write the word out instead of making lots of mistakes that there. So I would recommend you if you're doing, say, an exam question or a lab, you probably should do it this way, right there. You make fewer mistakes. So actually, at this point, we're ready to write our code. We've got our 37. If it's anything other than, if any of these bits are a 1, we're going to go ahead and go to 1. Otherwise, we stay in ground. So this code is actually very simple here at this point right here. So let's just go ahead and write the code for this right here, and it's going to be if in current state is equal to S2, right? That's where we're at. There. And we can go ahead and get our inputs is equal to port 0 ended with 0x30. I had 37 there, right? Right there. If inputs not equal to 0, then next state is equal to S1, else next state is equal to S2. And that's it. That one's a very easy one right there. Now you notice it gets a little easier as we do them. That there. So let me kind of go back and review this here. I mean, there, that there. There's a lot of material. This is and we're going to see this again. Trust me, we will see this again because next week we will be doing a lab where you're going to be doing a relatively straight, simple state machine. Before we can do the lab, we have to put in a delay process right there. That there. So in other words, what we're going to be doing is we're going to set up a timer, and the reason we have to set up the timer is, and we could do this actually without the timer, is in order to see what's happening on the boards, we have to slow our clock down right there. Because I'd like to see this happen on board, LEDs to show what state's out there. Now, the next thing here, and we'll come back next week and talk about how we handle the outputs. Because what we would like to see is see this actually work on a board out there, so that when we push a button out there. Now we've only got we probably won't do this in the lab. I did buy a bunch of buttons. I have to get a bunch of buttons. We can move wires in and out up there, but we'd have to handle debounce. I have to think about that. Let's just kind of review where we're at. Let's go through the process. Go through this again. Right there. All right. Here's our basic finite state machine. It's an elevator. This is elevator Bodo. It's probably at the Chancellery, right? This is probably the one that they have there. That's what I don't know how many floors. That's a huge building out there. It's 30 floors that there. So, I'd hate to be in the elevator and have to press 1, and then we can get to 1, have to press 2 out there, because that's the way this elevator is going to operate. So we have more work to do on this elevator out there, Great Moore State. But regardless, what we're looking at here is we're in state ground. We can either stay in our ground state or go to 1. When we're in 1, we can either go to ground or we can go to 2. or stay in 1. So we have 3 possible transitions in 1. When we're in 2, we can either stay in 2 or go to ground. So we haven't talked about our outputs, but our outputs are just simply, if we're going up, we take that there. If we're going down, up there. So we can look at what states we're going to be going up and that there. And what we're going to be doing is we're probably going to have to create a couple of additional states that are in that there, or we just simply send a pulse. Up there, and we put a delay. We'll handle how we actually move the elevator later. Up there. All right, getting on to our next page right here. I think this is the page that I skipped. Let me look it up there. Yeah, no, I skipped that page. This is the page that I came back and realized that we had 7 inputs right there. So this is the first page we looked at right here, and this is our transition, and we looked at to go from right there. I did this one a little bit reversed, but in order to stay at ground, we determined that all 5 of these inputs had to be low. If any of them are high, it's going to have to be up there. And so what we've determined is that we looked at those inputs in the order, and we came up with the fact that, and this is not very well written, but if we're in the current, we read our inputs, we ANDed it with that number, and if it's not 0, we go to 1. I left off here, this is a mistake, which, matter of fact, let me just rewrite this over here where it's a little clearer, is if current state equal state ground, right there, that's there, then we're going to, our inputs are equal to port 0 ANDed with, what was it, 6E, 6E, right there. If inputs not equal 0, and what am I doing here? Not equal 0, then state, or next state, is equal to S1, right? Else, and I left this off the first time through, that's why I'm redoing it. Next state equal S ground. Right there. So clean up your notes a little bit to incorporate the fact that I left this off the first time through. I remembered it the second time through, but the first there, because we have to accommodate the fact that there. And the reason is you can do this a different way where you don't use state next state and where you just simply state. And if you do that, then you don't have to bother changing it. I like to use state and next state. That way you know what, this is your current state, this is the next state you're going to, and you only change on, in our particular case, the only time we're going to change is at some rising edge of the clock. Actually, the only time we're going to change states is when our timer interrupts. We're going to do the timer interrupt next, and then whenever there's a timer interrupt, we're going to set a variable called change state. That's there. So that's how we're going to handle this, where you can see it in the lab. So every, once a second, the timer will go through, and then it will look at our inputs there. Otherwise, we have to accommodate deep bounds and all kinds of issues, and this will go through so fast we won't know what's going on. That there. So, all right. So going back to our next one, we repeated the process. That there. Actually, I did rewrite that with the else there. So I did take care of that. Although I did have a mistake here. I put the semicolon there. That there should not be a semicolon there. And then we redid this process with state 1, which was our nasty state, right? And the reason state 1 is nasty is because we have the else if required. This else if is required because we have multiple. Now just imagine how messy this would be as if we had 6 transitions in there. We don't want to do it this way. We're going to find a simpler way to do this, but right there. So we're looking at this right here. So that's S1. And then we repeated the process again. Right there. Oh, and then the last one was this right here. That's the last one. It's fairly straightforward. So all of this would be in our code. Now there's more parts of the code than this, obviously. We have to set up our input ports. We have to set up our output ports. We're going to have to do a timer, set up a timer in order to know when to transition. We don't want to constantly be doing this. We want to just kind of go through and look at these inputs only at certain time intervals. That there. And the only reason, in a real elevator you can do it constantly, but here we're trying to do this on a lab bench with non-debound switches and at there. So we'll set up a timer where we're only doing this once a second, where while it's one state you can move the wire in right there. So, all right, I'm going to quit at this point. That there, I think there's a lot of material here, isn't there? This is that there. We're getting into the nitty-gritty of how we would actually do control, though. We've kind of left all this introduction of the microprocessor and the microcontroller and how it works. We've left that aside. We've moved to the core part of this course, and that is how do we do things with this microprocessor? How do we make this do real work? Otherwise, if we understand how the microprocessor works and how all the registers, what good is it if we can't make it do something? Now we have to make it do something. In this particular case, we're operating the dumbest elevator in Kuala Lumpur. I don't know. There's probably some elevator that somebody designed this way. That there. This is definitely the short and easy way of doing it. That there. So, with that said, we actually today I ran longer than yesterday. Yesterday, both my classes were short yesterday.